হ্যাঁ বাবা, বাবা আমি ক্লাস নেব এনপিটিএল এর, পরে ফোন করছি তোমাকে 2 ঘন্টা। ওকে, টাটা। আচ্ছা। Okay, I'll start. This is the week 7 of TS session of Design of Steel Structures taught by Professor Damodar Maiti. I'm Trisha Chakraborty, one of the course teaching assistants of this course. I'm a PhD student at the Indian Institute of Science, Bangalore. I will start with a recap of the previous 6 weeks. That is, half the course is over and 6 weeks are left. There are two broad branches of structural engineering, analysis and design. There are two broad branches of structural engineering: analysis and design. Analysis is the forward problem. Here we are given the structural dimensions, the boundary conditions, and the applied loads, and we have to find the responses induced in the structures. Responses can be of the form of forces, stresses, and deflections and strains. Yes, Nikita, did you raise your hand? Do you have anything to ask?
Yes, ma'am. Good evening, ma'am.
Good evening, good evening.
Uh, Actually, ma'am, I have a question regarding exam.
What?
I have a question regarding exam.
Okay, okay. What is it?
Uh, will a core book be provided in the exam?
Uh, See, I don't know if the code will be provided, but I think you are allowed to use the resource. I mean, I don't know exactly if the code will be provided, but as far as I know, in any exam, in the question itself, whatever data you need, whatever you need should be provided. But
Okay, ma'am.
you can ask this question also in the in the channel of the course. If anyone else knows the answer, they can tell you.
Okay, ma'am. Thank you.
Okay. Yes, Ronik, you have a question?
मैम मुझे पूछना था कि
हाँ.
ये एग्जाम में नेगेटिव मार्किंग होता है।
एग्जाम का डेट फिक्स हो गया क्या?
यस मैम 26 अक्टूबर।
अच्छा
सॉरी
मुझे
26 अक्टूबर या
अच्छा, आई डोंट नो दैट। मैं पता करके मैं वो चैनल में लिख दूंगी या मैं अगले क्लास में बता दूंगी, ठीक है? मुझे एग्जैक्टली पता नहीं है मतलब स्कीम क्या है।
ओके मैम। ओके मैम।
पर वो एक डिस्कशन चैनल होता है ना कोर्स का, उसमें पोस्ट करके देखना एक बार। किसी ने प्रीवियस कोर्स लिया होगा तो उनको पता होगा। ओके, एनी मोर क्वेश्चंस राइट नाउ? ओके देन, I'll go on with the recap. Analysis. In analysis, we are given with the problem, and we have to find out the responses for that come in the form of forces or stresses and deflections or strains. And in design, it is the inverse problem, that we are given the loads to be withstood by a structure, and we have a basic idea, a basic like the architectural layout of a structure, that what is the purpose of the structure and the number of rooms and a basic layout, but and some criteria on maximum deflection as well, the serviceability criteria, and we have to find out the size and the materials of the structural elements. This is a course on steel design. You would have done a course on concrete design before. So why do we use steel? The concrete is the most versatile material for constructions. That is why it is used in most of the structures we see around us, like more than half anyway. But steel is a much stronger material than conventional. Yes, steel is a much stronger material than conventional concrete. That is yield stress and uh, please mute your mic. Is anyone there's some background noise coming? Okay. Its yield stress, ultimate stress, and all that will be and shear strength, not yield stress, yield strength. The a material is characterized by its yield strength and its ultimate strength, so that is higher for steel than in concrete, much higher. And steel also has a high strength to weight ratio, so steel structures are lightweight, and steel is ductile compared to concrete. So the area under the stress strain curve is larger in steel, and that means that it allows for a large amount of deformation before it finally fails. So that gives warning time, which is a very useful property to have in a structure. However, steel is much costlier than concrete. So, in residential buildings, in institutional buildings, steel is generally not used. Steel is more used in more specified structures, like towers, for example, or bridges. And why do we need design? The components individually and the entire structure should withstand the load throughout its lifespan, satisfying the serviceability criteria. Withstanding the load is the part of the collapse criteria, and this is the serviceability criteria has to do with the deflection, that the deflections in all the structural elements should stay within the limits. And lifespan is also, when you design a structure, the lifespan is simultaneously decided upon 50 years, 75 years, 100 years. And that is the suppose a residential building has a lifespan of 40 years or 50 years. That doesn't mean that it has to be broken down after 50 years. It means it needs major repair. You have to survey the structure properly again, see if it needs major repair, and then it can be continued to put in use. To properly design a structure, we have to ensure it is economical to construct it without compromising safety. So it has to be a cost-effective design. So you can't make it safer as much as you want. Then it will become very expensive. So there has to be a balance, and for that we need a proper knowledge about the entire design procedure. So, and the mechanical properties of steel, there are five of them, that the IS 800 2007, the Indian Standard Code for Steel Design, says that these five properties have standard values that we can assume irrespective of the grade of steel. And these are density, unit mass is a density, modulus of elasticity or the Young's modulus, the Poisson's ratio, modulus of rigidity, and the coefficient of thermal expansion. These five properties are to be taken at these values irrespective of the grade. And how do we define the grade? What it means is that the principal mechanical properties of structural steel are the yield strength and the ultimate stress, Fy and Fu. And this Fy is and Fu are what defines the grade of steel. So if the one of the most commonly used ones that you would have encountered so far is that if is Fe 250. 250 means that the yield strength is 250 megapascal, 250 MPa, and the ultimate strength corresponding to that is generally 410. But again, all these are not fixed. There could be combinations. And unlike concrete sections, in steel we use certain well-defined sections, like these are the cross sections. Like if you have a beam, this is the cross section, it will go into the plane, the length will go into the plane. In concrete, what did we do? We just put assume some dimension, for example 300 by 400, and we checked if it is sufficient or not. Here also the basic concept is the same, that we have to assume a section. For design we have to first assume a section, and we will see if it is sufficient. But in steel we cannot just take two dimensions and make it a rectangle or a square. In steel, this BIS, the Bureau of Indian Standards, it has it has a lot of a list of a lot of sections of specified dimension and specified shapes. All this, for example, this is a joist, an I section. All its dimensions, this depth, this is called the web, and this is called the flange. So the thickness of the flange, the width of the flange, depth of the web, and thickness of web, and all these, this angle, this is slightly tilted, all these data will be is standardized for particular sections. So if this section is called ISMB 2, suppose ISMB 200, these joists are named by IS something B, that something stands for large, medium or small. So ISLB, ISMB, those stand for I sections. So if there is a section named ISMB 200 in this standard, you will find all its properties tabulated. It's all these dimensions, its weight per unit length, geometric dimensions, and moment of inertia and all that. And 200 here stands for this depth, this depth D from top of the flange to bottom of this flange will be 200 millimeter. But that also will be mentioned, this D equal to 200 will also be mentioned in that code. So you don't need to go into the code knowing about this shape of these sections. You can just see everything will be mentioned. This is an I section, this is a channel section or a C section, this is an angle section, which is going to be very important for today's class, because we are studying tension members, and angles are one of the most commonly used tension members. This is a T section. These are hollow sections: hollow square, hollow rectangle, hollow circle, and these are some solid sections. They are not very commonly used. Mostly the ones they are used, but the ones you will encounter for this course and the exam are the I section and angle section mostly. And of course the plates we have already studied a lot. The plates used to connect bolts, and the plates used as tension members or compression members. This is the stress strain curve of elasticity. This is a specimen. It has for a tensile force is applied on it. The force is increased gradually. This force P, and the cross section area A. P by A, you know the stress at every point. You don't increase the stress, this tension continuously. You increase it at certain steps. So at every step you note down the force, from that you get the stress. And after every increment we have instruments called strain gauges. From that you can get the strain, you can measure the strain developed in this specimen. So we can plot the stress strain curve. I won't go into the details again, but I have already said. But briefly, this CD point is important for us because it is the yield point. That is what is corresponding. This stress is what the Fy is in our grade of steel. This is the yield point, because after this you can see that here the slope is very high. So it can take, for a very less amount of strain, the stress in the structure increases a lot. But after this the structure starts to flow, that is, it becomes plastic. So it is not elastic anymore, it has yielded. So a little change in stress brings about a lot of change in strain. So it is flowing. You can understand from the English word flow. So this is the Fy, and this E is the ultimate stress, the Fu, the maximum stress it can take. After that, this starts to fall, and then F is a fracture point. These are terminology, but these are very important, especially for exams like GATE. They often ask MCQs asking you to identify these points. Okay. These are some modes of failures of steel structures: bending, local buckling, shear buckling, web crushing and buckling, and lateral torsional buckling. Bending and shear we have already encountered in concrete structures, and buckling is a special type of mode of failure that we have not yet encountered in steel structures. And in concrete, it is not relevant, because in buckling, as I've said, buckling occurs in structures, in elements where one dimension is very large compared to the other two dimensions. That is what happened in steel structures. The sections are very small, the cross section area is very small, and the into the what the sections that I showed you, the I section, that was the cross section, and the beam goes into or out of the plane. That dimension is much larger, so it buckles along that direction, the longer direction. So this buckling will be relevant in compression members. So you can buckling is a phenomenon that happens only when the beam is under compression, or a column. We call that column. We call compression members columns. So that will be relevant in next class when we study compression members. Today we are looking at tension members. And deflection, all these were collapse criteria, all these were related to failure, what we perceive as failure. But deflection is another type of criteria entirely, the serviceability criteria, that that doesn't lead to failure or like collapse, but it also has to be satisfied. Collapse limit states and serviceability limit states both have to be satisfied. These are the design philosophies: working stress method and limit state method. IS 800 2007 revision works mostly on limit state. Whatever formula you have learned so far, you will see that you are applying a safety factor on you are multiplying the load with one safety factor and you are dividing the strength with one safety factor. So this is what limit state design is. The design action, that is the working action multiplied by a factor of safety, has to be lesser than the design strength, that is the actual strength of my section divided by a factor. And why do we do this why are we giving these factors? We do this to approximate our design on the safer side, because there are many factors that are not under our control. There are so many things that, like, we are saying that this steel has a yield strength of 250 MPa, but it has been mass produced in the factory, so we don't know if every specimen produced from that factory has exactly 250. Sometimes something may have 240 MPa, we don't know. So to counter, and then the loads also, we are designing for a certain amount of loading that we expect to come, but under an extreme condition like an earthquake or an extreme like a cyclone, extreme wind loading, extreme earthquake loading, or overloading in live load, anything can happen. So to account for all these uncertainties that we cannot have complete control over, we apply these safety factors, because the first priority of design is to make our structure safe. Connections, the first few weeks we have looked at connections, and connections are very important in steel structures, because as I said that the sections that the sections are the rolled sections, they are directly produced from the factory, brought to the site, and then they have to be assembled. Unlike concrete, in concrete what do we do is we make a form work and then we cast the concrete together, like we pour the concrete, let it set, so then the beams, columns, slabs, foundation, everything is cast as a whole integrated structure. So there are no connections. The beams and columns are joined, they don't need to be joined together separately. But in steel, all the sections, the beams, columns, or multiple beams at one junction, they all have to be connected, and it is very important that the connections should be like enough design, because connections are the ones that have, it has been noticed that in failure of steel structures, connections are the ones that fail most often. So, standard parts are properly connected to create the steel structures. The connections make up a large amount of the cost of structural steel. So, connection design should be given top priority for both safety and structural economy. The two types that we have looked at are bolts and welds. By now, you should be very familiar with these. This is the shank of the bolt. This is the head. What do they call it? And and this is the nut that we have to screw it to tighten the bolt. And we know there are two types of bolt. There are shearing and bearing type bolts, and then there are friction type bolts. Mostly you would have encountered bearing and shearing type more, but friction grip types are also important. And welding is works in a different way. In bolts, this bolt is a separate entity from the plates, but in welds we have this plate, and then we take the mother material and we put metal here, and then we melt it, and then once it cools again, this entire thing is an integrated part, so they stick together. Now we move on to tension members. The types of tension members we have looked at in last class. There are three types of failure mainly: the yielding of gross section, rupture of net section, and block shear failure. All these three will have certain criteria. So every you will be suppose in an analysis, what do? We are given the structure, so you will be given the plates, the bolts or the welds. You will be given all the dimension and all the grades of the steel of the plates and bolts or welds, and then you have to find out the capacity of the section in each of these. So you can find that if yielding of gross section occurs, how much stress can this my member take before yielding of gross section occurs. Similarly, you will find one strength for rupture of net section and one strength for block shear failure. And the strength of that tension member is the minimum of the three, because you can understand that if it yields at 100 MPa and if it ruptures at 50 MPa, so the strength you have to take the minimum one. At 50, it will already rupture, so it won't go up to yielding. So you have to take the minimum of the three. And the other type of problem is design, where you will be asked that you are suppose some things will be given, like these two plates you want to connect, and I need it to take a load of 100 MPa. So then we have to propose a design, we have to propose an arrangement of bolts and welds. We have to check if all these three criteria are greater than 100 MPa. If it is, then it is fine, I can allow my design to go ahead. And if it is not, if we find that suppose the strength in block shear failure is 80 MPa, then I have to give some additional bolts, or I have to increase the strength of the bolts, the yield strength of the bolt. I have to do something, and then or I could reduce the pitch of the bolts. All of these that work. Like if it falls short, you have to give it some additional strength. There are many ways you can do it. So you can do have to do something, then you have to again check that all in my new arrangement, all these three stresses should be greater than what I want my section to take, and then you can allow it. So this is an iterative process design, and design does not have a single answer. So in analysis, if you are given an arrangement and you are asked to find out the strength, everyone will reach the same answer. But in design, two or three people can reach very different answers, and there's nothing wrong with that. These are some visual representation in yielding of gross section. In this type of failure, the yielding of gross section occurs. A significant amount of deformation occurs before the material actually fractures. So the deformation makes the structure unserviceable. This is an I keep on saying there are two limit states that we are looking at: collapse limit state and serviceability limit state. Collapse limit state has to do with the stress strength part of it, and serviceability limit state has to do with the deflection or strain part of it. So here what happens is yielding, as I said, as you saw in the stress strain curve, once the material has yielded, the strain increases rapidly. A little change in stress requires a lot change in strain. So what happens is the structure starts to flow, there is a lot of deformation, and the structure becomes unserviceable. So this is called yielding of cross section. TDG, this value is called the strength in this criteria. And then the second one is rupture of net section or fracture, TDN. This is a collapse limit state. When the net section of the member reaches the ultimate stress, then rupture or fracture of member takes place. Here, it is not. It does not have to do with yielding or more like strain increasing rapidly. Here we have to look at the gross section. That is the, the what the gross section is, the section of the whole plate. Yes, Nikita?
Ma'am,
Yes?
you do not do assignment based questions in this session?
Uh, I can if anyone asks me, but I generally solve problems that, like external problems. If you have
Okay.
any doubt, you can ask anytime.
Okay, ma'am.
Okay.
Excuse me, ma'am.
Yes?
Is there any chance or probability that the assignment question will appear in the upcoming exam?
See, I don't think it will come exactly with same values, but it is very likely that the pattern will be similar. Like with different values, a little bit of modifications.
Like there will be some alterations, right, ma'am?
Yes, will be some.
Alterations.
Yes, yes, yes. They won't. They won't. I mean, I guess I can't predict what will come in the exam because I'm not setting the paper. But I would guess that they won't give the exact question. They won't give the same values because then that's defeats the purpose if you're understanding.
Yeah, ma'am.
But I would suggest that you should solve all the assignment questions because the pattern is bound to be very similar. But these there are only certain types of questions that can come in these courses. Design courses are relatively very limited, so there are only certain categories of questions, and they are bound to ask within those.
So, can we focus the assignment questions mainly, or like,
See,
could
there
you
are
please let
questions.
us
Yes, tell me. Could I
could you
please?
please let us know if there is anything specific we can do to succeed
Yes.
in this course other than. Mm,
Yes, the first thing is Professor Damodar Maitha actually taught me in my college. So his entire NPTEL course we did that. He solves. You have noticed that in every class after with every topic he solves certain questions step by step. Those are very important. So those, I
yeah,
think,
ma'am.
when you go through the lectures, try to solve every question on your own. Like see the solution, but then work it out once through your own. Only then you will see that you are not missing any step. Okay.
Okay, ma'am.
So entire course you should do that. And apart from that, you should go through the assignment questions, try to solve those. I think that should be enough. There won't be any out of the box tricky questions. Still
So
design.
assignment takes. So assignment questions are just like test series questions, like, right, ma'am?
Uh-huh.
Like we have to go through all the courses syllabus given on the course and assignment questions are just
And
like case
additional.
series questions. Yeah, yeah.
Yes,
I got
yes.
it.
But the ones included in the lecture itself are the best ones. They cover everything. They cover all the topics very properly.
Okay, ma'am. Thank you.
Okay. Any
Excuse me,
more
ma'am.
questions? Yes, yes.
Ma'am, can you explain the unit-wise weightage of marks?
Okay, I don't know that right now. I have to just go through the exam pattern once. Okay. I will. What do you mean by weightage? Topic wise.
Yes, ma'am. Topic-wise, ma'am.
Okay, I don't think there is an official topic wise weightage, but I have a very good idea about how the weightage will be. Like I can't say numbers, but the most important topics if you want to know, connections, especially bolts, welds also, bolts and welds, and tension members and compression members. Mostly connections is the most important topic, then tension members, then compression members. And then there are many other lectures like gantry girders and I think eccentric connections, and there are several.
Okay.
Eccentric connections is a little advanced topic. I would say that up to compression members you should do very well, where you should know everything. But after that, there are several, like last few lectures are very specified kind of structures. They, if you
Okay.
don't have, if you have time, you should go through them. But if you don't have time, you could, if you want to give less weightage, to those would be the ones. They will probably not ask questions from those last few lectures.
Okay, ma'am. Ma'am, one more question.
Yes.
Uh, how many questions will be there for 1 marks, 2 marks, and 4 marks?
I'm sorry, I don't know that. I have to then go through that once and also ask this question in the channel, okay, the conversation channel. I think someone
Okay,
will
ma'am.
know that, or else wait, I'll just note this down.
Okay, ma'am. Thank you, ma'am.
Okay. I'll see if I can get to know this and I'll let you know next class. Okay. Any more questions right now? Okay. Okay, so this criteria is of the gross section, that is the section of the plate as a whole, and a rupture of net section occurs in this section where the bolt hole is. So this is one of the critical sections. The net section, what does it mean? That this was the width of the plate, and then the this part is a bolt hole. So that part is missing. So the cross section area effectively, or the net section, reduces. So this is a critical section where fracture occurs. And there is another type called block shear failure, TDB. Here a segment of the block of the material at the corner of the connection, like this, like along the boundary of the connection, shears out due to possible high bearing strength of steel and high strength of bolts. So what happens is the plate itself does not fail, the bolts itself do not fail because they have higher strength than what is required to make them fail, but there is some kind of shear acting as a whole along this boundary, and that shears out. So the steel of the plate isn't failing, the bolt isn't failing, but the section is failing as a whole. So this is another criteria that will be clear as we do questions. And for design of tension members, we have the design strength of the tension member is a minimum of the three, that as I said. Let's look at an example. Determine the design tensile strength of plate, 150 mm width and 12 mm size. 115 to 12 mm means that, see, this is the length. Okay, this can go as long as this. The length is undefined, but this diameter is of the dimensions. If you see two dimensions are given, that means that the cross sectional dimension is given. So this plate that you can see, this, if this is the plate, this is the cross section. So 150 is this width, this width, and this thickness is 12 mm, and this is the view that you are seeing. Okay, and it has bolt holes of 16 mm diameter. These four bolts, the arrangement is given. So this question, they have told you to determine the design tensile strength. So this is a question of analysis, because the entire arrangement is given, all the grades of steel, everything is given. You have to find out the design strength. Don't get confused seeing this word design. This is a question of analysis because it can have only one answer, and you are given the arrangement and you have to find out the strength. So the strength, I have to find out the strength in each of these three criterion. So these are the formulas that you will eventually remember. Like you will memorize these. You don't have to sit and memorize. I my understanding says that these formulas should be provided, but they might not be. So once you do a few questions, you will automatically remember those. These are not very like great difficult formulas. The design strength due to yielding of gross section is AG, that is the gross area. What will be the gross area? 150 into 12, because this is the cross sectional area, this is the plate, this is the cross section area, this entire area. So 150 into 12, and the yield strength here is given. See, Fe 410 is the steel, so 410 is yield strength, and 250 is the 410 is the ultimate stress, and 250 is the yield stress. So Fy is 250, and what is this gamma m naught? It is the factor of safety that I am applying on the strength, that is 1.1. This 1.1 is got from the code. So this 4 to 1 1800 is the area, 250 is the yield strength, and 1.1 is the factor of safety. So 409 kilonewton is my strength, design strength due to yielding of gross section. Now I will look at rupture of critical section. Design strength due to rupture of critical section is, it has a point 0.9. Whenever you will generally see that whenever the Fu term is used, the ultimate stress, there is a point 0.9 factor that has something, that there is some kind of research work behind this. So this is the formula: zero point 0.9 into Fu into An. This is the area of the net section. So see here, there are two bolts here. So if you look in this way, in the net section you will see two bolt hole diameters are cut from this part. So this is 150, and from here 16 and 16 are missing. So 150 minus 6. Okay, and another thing is that the bolts have diameter 16 mm, but the bolt holes have diameter 18 mm. In the code, there is an approximation like this given, that you have to add 2 mm to the bolt diameter to get the bolt hole diameter. Yeah. So this is 18 mm, so 150 mm, then you have to separate 18 mm and 18 mm. So you will get, and this part, see this formula you would have already seen in this sigma p square by 4g is due to staggered bolting. Staggered means that these are in parallel lines, but if there was a bolt here, like if this was like a diamond shape pattern, then this part would come into the picture, staggered bolting. This is not valid here, this is 0. So 150 minus 2 into 18 into 12, this is my effective width, and the thickness remains 12. So this is my effective area, net effective area An, and you apply this zero point 0.9 into this area into 410 by 1.25. And again, this, see, in the code, you will, and yes, I would suggest all of you to go through the parts, that the entire code is very long, but the topics that have been covered here, you should just one go through, then you will see all these things, that in in yielding, say, gamma m naught is used, that is 1.1, but in fracture gamma m1 is used, this factor is 1.25, the safety factor. See, these safety factors are, again, you will find no reason or calculations behind these. These are empirical work, but these are the result of a lot of research, and they are presented in a very simple step-by-step format in the codes, so that anyone with basic knowledge can design. Okay, and now we are finally, and this strength is 403 kilonewton. This is less than this one, so already we can see that this is not going to be my critical strength. And let us see block shear strength in this. For this, the gross area in shear is, see, this, if it shears off, if the block shear failure occurs, how will it occur? It will occur like this. Okay, this part will tear off, like you have to join the bolts, you have to make a rectangle sort of thing, this will shear off. So the gross area and shear will be 65. This length is 65, this is 35. So 65 plus 35 into 12, this face you can imagine that if this part shears off, if this part shears off, there is a cross section area that where the thickness is into the plane, the 12 mm is into the plane, that you cannot see in the 2D view. So again, if this is the part you are seeing, if this is a block that is shearing off, if tearing off, you look at this, you will see the 12 here, and the length is visible here, 65 plus 35. So it is 1200 millimeter square, and the net area in shear, you have to subtract the bolt diameters. So 1.5, you can see that you are taking this from the midpoint, but this is entirely included. So for this we will take 9 mm, and for this we will take entire 18 mm. So this is 1.5 into 18 into 12, this is the net area. 1.4 bolt holes are getting intercepted in shear areas, and the gross area in tension is this this dimension is 42.5. Why is it 42.5? It's this the pitch is 65. The pitch and gauge are both 65 here, and this entire length is 150. You won't be given this 42.5. You will be just be given the pitch and the gauge and the end distance and the edge distance. You know that this is this the distance between these two is the pitch, and this is the edge distance. So edge distance is 150 minus 65 divided by 2. So this the gross area and tension is 42.5 into 12, and the net area and tension is, again you have to subtract half a bolt hole because it is this part of it. This part is in shear and this part is in tension. So you have to subtract half a bolt hole, 42.5 minus this half bolt hole 9 mm into 12. The block shear strength is a minimum of the following. There are two types the block shear filling can occur: shear yield and tension fracture, and tension yield and shear fracture. These formulas are just the see here the shear yielding is all these formula you have encountered individually before when you were doing when you were studying bolts you would have seen these
Ma'am,
formulas. Yes,
excuse me, ma'am, one confusion.
yes,
By sharing area, you mean that 65 mm plus 35 mm up to that part, right?
yes, yes.
So the rest part, it will be 35 mm, right? It will be,
You mean this part?
yeah, that part will be free, right, ma'am?
No, the
Like,
tension. No, this. Repeat again.
by shear area, you mean that 65 mm plus 35 up to 65 mm plus 35 mm.
Yes,
That area is shear area, right, ma'am?
yes. This part is a
So
shear
the
area.
joint, yeah, jointing will be there, right, ma'am?
Yes,
So the rest part
but yes, but I think there's a problem with
will
your
it be,
mic.
ma'am? Free?
Your can you repeat
It,
it? Your mic got like I couldn't hear in the in between. The shear, yes, the shear part is this part,
yeah,
and
yeah, that part and the remaining part, ma'am. It be free? Like the jointing will not be there, right, ma'am? It will stay as a individual free, like for one plate only.
yes. Okay, I'll show this figure.
Like, ma'am,
This see, this is the shear area, and this is the tension area.
yeah, yeah.
Okay.
Actually, two parts.
I don't get your question exactly. Do you mind writing the question in the chat box, or you can try explaining it again.
Like, ma'am, the plate total dimension is 135 into 12, somewhat like that, right, ma'am? 135 into 150, and the length is 65, 35, and the right one it will be 35, right, ma'am?
Yes, yes. This one will be 35. Yes,
35. So the sharing part is up to 65 plus 35 mm from the left side.
yes, yes.
So what I mean is, ma'am, are we assuming it as a beam, ma'am, to be attached on the beam? Is
See,
this
we
plate?
no. This plate is okay. Okay, this plate. No, it is not attached to. Yes, you can call it a beam. These plates are like this. There will be one plate. There will be
So
another plate.
is it going to be attached through beam, or like
No,
the concept, ma'am?
it can be attached to another plate, and this can like what we did during bolting was we had two plates, and they would be overlapping, and we would drill the bolt hole here, right?
Yeah, ma'am.
So this plate here that we are seeing, it has another plate below it or above it. That is where the bolt is
Okay,
connecting.
ma'am.
And what you call a beam is up to you. A beam is a structural member that transfers bending moment and shear force. So this will we don't call it this a beam, but see beams the way we perceive in concrete structures are not the same like we perceive in steel structures.
That's
Okay.
a common, right, ma'am? Yeah, ma'am.
So
But
yes.
yeah, yeah, ma'am, I got it. So we have to take it as a common, right, ma'am?
Yes, we have to
Not
take
for
it.
particular, like we cannot assume it as a beam or column to be
No, 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 no.
attached.
You are taking it
Yeah,
as a
yeah.
you are taking it as a solid section, and remember this might not be a plate. This might be an angle section. This might be an
Angle.
angle section, and this is the part that we are studying. Okay.
Yeah, ma'am.
Anytime an angle. So this is, we are calling it a plate, but it is basically just a solid rectangular section.
Okay,
Okay.
ma'am. Yeah, ma'am.
Okay. So for the shear yield and tensile tension fracture, this is the one combination. You have to find out these four areas first: gross area and shear, net area and shear, gross area and tension, and net area and tension. What happens in this formula? You will see that the combination is always with yield strength we multiply the gross area, and with ultimate strength we multiply the net area. Okay. And when there is a question of shear, a factor of zero point 0.3 comes below, because there is some one misses criterion. Again, all these are empirical formulas. The derivations are not shown in the codes, but you have to remember these, like they are presented after a lot of research. And when there is an ultimate strength, the zero point 0.9 factor comes. So this is how you can remember it. These are just trends that we will see in the code, that yield strength is multiplied with gross area, and ultimate strength is multiplied with net area. And when there is ultimate strength, there is a factor of zero point 0.9, and when there is yield strength, there is a factor of root 3 in the denominator. And again, the factor of safety is also vary. For yield strength we have a lower factor of safety 1.1, because it is, in a sense, you can say it is less critical, because ultimate strength mean it is tearing off, it is completely collapsing. So the factor of safety is higher to approximate it safely. So this formula for shear yield and tension fracture, for shear there is yielding, so 250 into this shear gross area and shear is 1200, and these are the factors. And for tension, you are taking 410 the ultimate strength, and you are taking the gross area in, and sorry, you are taking the net area in tension, so it is 402. From this we are getting 276. And tension, yield and shear fracture is just the opposite. So for tension we are going to take yield strength and gross area, that is 510 from here. And okay, sorry, 1 second. I think there is no, it's fine, it's fine. This zero point 0.3 comes in for shear, and the zero point 0.9 comes from the ultimate strength, so it is fine. And so here both these factors come in this side, because for shear and for fracture. And a vn is the this net area and shear multiplied by the ultimate strength. See here, the ultimate strength and then this fu and fy will be same for both shear and tension. Okay, because we are using, because it is the same material, this is one steel material, that whose strength we are calculating in yield and in tension. But since the material is same, the uh, yield strength and the ultimate strength will be same for both. And these are the, from this you get 265. So you can see that tdb, that is my strength, my design strength in block shear is a minimum of these two, that is 265. And the strength of the plate, the design strength of the plate, is a minimum of all three: 409 from here, 403 from here, and 265 from here. So 265.2 kilonewton is the design strength of the plate. Okay, this is see, you were asking earlier. This is how the connect. We are only seeing this part. Like, this is an angle. This see, this is the one leg of angle that is attached to this gusset plate. This is a gusset plate. On top of that, there is one leg of angle, and the other leg of angle is sticking out. Is sticking out of the computer or laptop screen. That is shown in the form of this thin section, and this is the leg that is attached. Okay, so and this is the side view, which I always recommend you imagining. This is the gusset plate, this leg of this angle, this flat leg that we are seeing here, this is the leg, that is attached. So these are the bolts, this is the bolt line, and this is the outstanding leg of the angle that is sticking out. So, and an unequal angle, ISA 19 to 16 to 6 is connected to a 10 gusset plate at the end with four 16 diameter bolts. The angle is to be used as a tension member. Find the design tensile strength of the angle. If this is an unequal angle, ISA is Indian standard angle. Corresponding to ISA 90 into 60 into 6, you will find all its properties in that BIS book. I could probably show that. SP61. The code's name is SP61. if these are all the lists of, okay, this is an eye section, this is a channel section, so I have to find out angle sections. I hope this code is visible.
Yes, ma'am.
Okay, thank you. So angles, single and doubles. Rolled steel unequal angles, that is what we are looking for, so it is in page 12. See, these are ISA, and we were looking at, uh, see, this is 3020, it is written in this format. So what I'm looking for is ISA 9060. See, this is ISA 9060. This is the angle I'm looking for. It has one leg as 90. This A and capital B are marked here. This is the angle section. Capital A, this is 90. Capital B, this is 60. And the thickness can also be of four varieties. ISA 9060 can have four variation. We are looking at 6 mm, where the thickness is 6 mm. So we are looking at this part. So the thickness is marked here. That thickness T, it is shown as this thickness, okay, and this thickness, the entire thickness is constant. So this thickness, this part is 6 mm, one leg is 90 mm, this is 60 mm. And you can see all the properties: sectional area, weight per unit per meter, center of gravity, that is the CG from this point. All these quantities that are written, CXX, CYY, EXX, EYY, all these quantities will be marked here. Though this is a PDF, so these marks are not very clear. But if you can find a better quality PDF, all these will be properly visible. Then the moment of inertia, and these are spread over two pages. Okay, so you will see that the code is like this: is the left page. The left page will have the picture and the name and the designation, and then you will follow this row and you will find out all its properties that will run into the right page. So the right page, this is the topmost one. So this line, it has radius of gyration, it has modulus, this z, I mean plastic modulus, if you know about these. So all these are properties of C. And last, again, the designation we mentioned, ISA 9060 6 mm, this top one that we are looking at. I just showed you, you won't need it in this question, but I just showed you this is how you read codes, and if you are later going into the industry, you will need these. So this is what my angle. And see, if to connect this angle to this gusset plate, you can connect this 90 mm leg can be connected to the gusset plate, and the 60 will be sticking out, or I can stick the 60 and let the 90 stick out. That is up to me. So they are saying that uh, we are these are two combinations we are going to be looking at: 90 mm connected to the gusset plate with gauge. The gauge is this, okay, this distance, as not the gauge, this is actually just a distance that they have marked in this figure, is 50 mm, or 60 mm leg is connected to the gusset plate, and this G will be 30 mm, because this is that 60 or 90 part that is attached to the gusset plate, right? So if this is 60, this G can be 50. This is basically along the center line. 90 mm leg is connected to the gusset. I'm first looking at this case. The strength of section will be minimum of these three. So design strength due to yielding of gross section from steel. Okay, we do need this after all. From steel table for ISA 9060 into 6, AG is 865 millimeter. Let's check. Yes, see, this is 865. It is written in centimeter square, so it is 8.65 centimeter square, that is 865 millimeter square. So you get this cross sectional area directly as 865. And TDG is very simple, the formula: gross area into yield strength divided by 1.1. Design strength due to rupture of critical section. Here, this beta is a tricky calculation that is only used for angles. If it is a plate, if it is mentioned a plate, you don't need to calculate this. But rupture critical section has a beta. This term you have already encountered: zero point 0.9 into an fu by gamma m1, we have already seen for the case of plates as well. And we can just see that 90 minus 6 by 2 into 6, this is the area, net area of the connected leg. Net area of the connected leg is, this is my connected leg. Here the 90 is connected, and minus 6 by, okay, I'm not entirely sure why they are subtracting 6 by 2. It should be 16 by 2, right? One second. Okay, there would be something in the formula that I'm missing. It's probably in the formula that the width minus the thickness by 2 into thickness. This is 522, and gross area of the outstanding leg. For the connected leg, you have to see the net area, and for this you have to see the gross area. 60 minus 6 by 2 into 6, and the beta has a formula in the code. Beta is 1.5 minus 0.076 v by w by t. What is w is width of the outstanding leg. So here 90 is the connected leg, so 60 is the outstanding leg. 60 by t is normal 6 and fy by fu, that will be 250 by 410, and bs by lc, these are a little critical. Bs is the shear leg width, that is w by, see, this shear leg width is this. This wt is wi is this length. Okay, so it is 50 here, so it will be 60 is the width of the outstanding leg, 60 millimeter. Wi is 50 minus thickness, this, and the lc is 3 into 50, that is, it is this length. Lc is the end to end distance between the center of the two extreme bolts. So this is 50, this is 50, this is 50, so this would be 150. This is the, now we put this in the formula and we get this factor, and then you have to just put this in the formula to get this formula to get this additional term. You will see this term is 83 here, so 237.93. So if this was just a plate, my design strength due to rupture of critical section would be just this term, but since this is an angle, we are adding an additional term. And for block shear failure, failure may occur along the section 1, 2, 3. So for 60 diameter bolt, the D knot, the bolt hole diameter is 18 So tearing length in tension is 90 minus 50. This is 90 and this is 50. So for block shear failure to happen, it will happen like this, right? So this is 90 and this 50 is getting subtracted. So 90 minus 50, gross area and shear is 150 into 35 as plus 35 as we did, 150 into plus 35 into the thickness, that is 6 This is 1110 millimeter square, and the net area in shear is 150 plus 35 minus 3.5 into 1 by 1 point. Why is it 3.5? Because if you look from this center to the end, 1, 2, 3, these three bolt diameters are completely added and this half is added. So 3.5 into the bolt hole diameter, this, and the gross area and tension is like this. Tearing length in tension is 90 minus 50. This is 90, this is 50, so this part is the tearing length in tension. So 40 into 6 is the gross area in tension, and the net area in tension is, you have to subtract again half a bolt hole because there is only one line of bolts. So this part minus this part, this radius, so 40 minus 0.5 into 18, 186 millimeter square. Then we apply it in the normal formula, shear yield and tension fracture, and tension yield and shear fracture, and you have to see the minimum of the two. This is exactly the same. See, the only additional difference in angle section is that in design strength due to rupture of critical section, this factor is added. Apart from that, everything is similar, and you have to take the minimum of the three, so you get this. And with, even if you attach 60 leg to the gusset plate, the procedure will be exactly the same, and you end up with this. So you can see that here the strength with the longer, with the wider leg attached to the gusset plate, has a larger strength than this one. So generally, if you have the choice, you will attach the wider. If for an unequal leg angle, there are equal leg angle as well, like ISA 30-30, ISA 60-60, where both legs will have same width. But if they have different width, you would prefer to attach the one with the greater width to the gusset plate. Okay, there were some additional example, but I think we have covered most of the, like, most common two types of questions. So if you have any question, you can ask now.
Hello, ma'am. Am I audible?
Yes, yes, you're audible.
Hello. So, ma'am, recently I went to a construction site and I have seen a lot of ISMB used,
Okay.
usually mainly at the top portion of the buildings.
Okay.
So, here in this course, what we are studying is where will it fail, how much load it can take, how much strength it can withstand.
Yes.
So, my question is, ma'am, actually, what ISMB are used mainly on the upper portion of the building? Like, as far as I am concerned, I have seen them using mainly on the top portion of the building.
Okay.
So,
And
what might be the reason?
what were they using in the bottom part of the building?
Bottom part, like those brickworks, etc.,
Brickworks. Brick
like
is generally
concreting beams, concreting RCC beam columns.
okay. So you saw a building with which was a mixture of steel and concrete. So the
Yeah,
bottom
ma'am.
part was oh
Recently I went to a construction site
okay.
and I have seen a lot of like ISMB mainly used in the upper portion. Like, suppose for example, we have a 10-story building.
Hmm.
So up to 8 story, the building it is actually structured with RCC beams and column.
Okay. Okay.
So from ninth and at the ninth and tenth portion of the building, the
So
ISMB are mainly used. Those
okay. Okay.
plates, those bowls, etc.
Okay. Okay. So
What
firstly,
might be the main concern? Yeah,
yes, I see. Firstly, I have never heard of a building made of constructed of both, but that is a very interesting idea, ma'am. A very interesting idea. But there are two reasons that I can think immediately that why you would use steels in the top and concrete in the bottom is that, as I keep saying, that concrete buckling is not an issue. You know what buckling is, right?
yeah,
So
yeah, ma'am.
buckling is when you are under member is under compression and it is a slender member. There is a slenderness ratio in Euler beam theory. There will be a
Yeah,
slenderness
ma'am.
ratio. If it is a slender structure, it will buckle. And in concrete structures, buckling is concrete members, buckling is not a main issue because in the cross section area is large. In you will see the columns in 10-story buildings will have quite large dimensions like 600 by 1000 you will see some columns sticking out into the room, so the dimensions are very large. So buckling is not an issue as much with concrete, but it is a very important issue with steel. So when we look at modes of failure of steel elements, there will be lots of buckling modes. There will be local crushing and buckling, there will be web buckling. So the web part in the ISMB is an I section, right? So the web part is
Yeah,
the
ma'am.
this part, this buckles. There are there in during when we look at compression members, we will see certain criteria on the buckling. So it could be that you can see understand that if you look at a tall building, that the most compression is faced by the columns near the bottom, right?
Yeah, ma'am.
Maybe to since compression is such an important criteria in steel, maybe that's why they are using in the top and in the bottom they are using concrete. That could be one reason. And another advantage of steel is that it is very light. Light is a relative term, but steel has a high strength to weight ratio. So using steel in some parts, even though it might increase the cost, it could reduce the dead load on the body. The dead load is a self weight of the structure, right? So maybe
Yes,
adding
you
steel
got it,
at
ma'am.
some parts is overall creating an effect of reducing the weight, but the entire structure making it out of steel would be too costly, or buckling is also an issue.
Okay, ma'am. Thank you.
Okay, thank you. Welcome. You're welcome. And it's a very interesting thing. I have to look into it. I've never
And
been
ma'am,
through
one
it.
more apologies, ma'am.
Yes.
Thank you for sharing, ma'am.
Thank you
I have
for.
one apologies, ma'am. Since I stay at hostel and the dinner time is scheduled for 8 p.m.,
Okay,
ma'am,
okay.
I think I won't be able to continue further, so I have to
No,
leave. So sorry
yes.
for the
No,
inconvenience.
it's fine. It's fine. I would be
Thank
in.
you, ma'am.
Okay, okay. Thank you for attending. And are there any more questions from anyone? Okay, then I think we have covered mostly everything.
Yes,
Next.
ma'am. I have a question, ma'am.
Okay, okay. Ask.
Is river connection is still using or outdated?
Which rivet connection is outdated right now because you will see it in some old books, but mostly in IS 200, IS 800 2007 revision, you will see very less focus given to rivets. Mostly it is focused on bolts and welds only. So rivets are not relevant right now. You won't be asked on that, and it's not used anywhere now.
Okay, ma'am. Understood, ma'am.
Okay. If there are no more questions, I will be ending the class now. Next class, we will look at compression members. Okay, I'll end the class then. Thank you for attending.